Watch this small app. It allocates 1,000 objects every loop. The memory bar climbs steadily. No de allocación. That's a leak. Now who cleans this up? The garbage collector. It's built into the runtime. Java's hotspot, .NET's CLR, V8 for JavaScript. They run automatically at intervals. They start from roots like global variables and stack frames. Then they trace all reachable objects. Anything not reached is dead. The collector frees that dead memory. It does this in the background, so you don't call delete. But it doesn't know the intention behind your data. It only knows what's still referenced. That's why GC can be both helpful and dangerous. In the next part, we show why garbage collection is essential. The collector also handles fragmentation, consolidating free blocks into larger chunks. This keeps memory usage low without manual intervention. However, GC pauses can jitter performance, especially in real-time systems. Manual memory bugs kill productivity fast. A single leak can grow 5 megabytes per instance, piling up to 200 megabytes in a long-running service. Developers chase a 1 millisecond crash that happened on the 40-second run. Double-free bugs trigger undefined behavior, making binaries crash unpredictably. Pointers dangling after object destruction lead to 10 times more crashes on production. Memory corruption also opens security holes. Attackers exploit overwrites for code injection. Repairing these bugs costs 3 to 5 hours of debugging per incident. Each crash costs the company hours of downtime and revenue loss. Garbage collectors eliminate these headaches by tracking live objects automatically. They guarantee that stale memory never leaks, freeing developers to focus on features, not heap hygiene. GC also reduces memory footprint, often cutting usage by 30% compared to manual pools. In short, GC saves time, money, and hard-to-track bugs. Thus, GC is a critical safety net for modern applications. Mark and sweep starts by walking the object graph. A root pointer, say main, flags reachable objects. The algorithm tags each. After the walk, it clears untagged memory blocks. Think of 10 objects, 3 reachable, 7 collected. Next, generational GC splits memory into young and old. New objects live in the young generation. A minor collection runs often, freeing most dead objects. If an object survives 10 minor cycles, it moves to the old generation. Major collections scan both generations, but the old one is sparse. The code below shows a small Java program. It creates 20 objects, discards 12, then invokes system.gc. Observe the console prints. Minor GC, 12 removed. Later, a major GC logs, major GC, 18 removed. This demonstrates how the algorithm reclaims memory efficiently while keeping hot objects alive. Sometimes the GC misses, and memory keeps piling up. For example, a listener that never unsubscribes holds onto a window reference. After the window is closed, the listener still lives, so GC can't free it. That's a memory leak. Another common scenario is caching large data structures without eviction. If the cache grows unchecked, the heap fills and the app slows. Leaks show as increasing memory usage over time, spikes, or crashes. How to spot them? Use a profiler that highlights retained objects. Look for long-lived roots pointing to huge arrays or image buffers. Also monitor object allocation rates. And check event handlers that keep references alive after UI removal. Once you see a steady climb, you know GC isn't doing its job. Fix the reference, and the memory drops back to normal. Now here's what actually moves the needle in production. Start with heap sizing. Most apps run defaults. Change that. For Java apps handling payments, adjust your settings. Set heap between 40 to 60% of available system memory. Specific example, 16 gigabyte system, try 6 to 8 gigabytes heap. That shrinks GC pause cycles immediately. Next, garbage collector algorithm choice matters. G1 GC handles modern workloads better than older generational collectors. ZGC delivers sub-millisecond pauses if latency is your constraint. It costs extra CPU but eliminates jank. Third tactic, object pooling in hot paths. Don't allocate arrays in every request loop. Reuse them. This cuts allocation pressure hard. Finally, measure it. Use JFR or APM profilers. See actual pause times. Tune blind and you're guessing. Settings depend on traffic pattern, object churn, and latency SLAs. Most developers set it and forget it. That's fine. But if you're hitting GC pauses, test different settings in your staging environment first. Start simple. Heap size, GC type, pause targets. Measure before and after each change. One team dropped tail latency by 40% just switching algorithms. Your app isn't generic, it has unique patterns. Garbage collection is a lever. Pull it, see what moves. Then optimize for your specific traffic. Don't guess. Test with real load. Monitor the metrics you actually care about. Pause time, throughput, memory footprint. Different levers move different dials. What works for microservices won't work for batch processing. Get specific. Change one thing at a time. Document everything. Garbage collection isn't magic. It's a tool you control. Own it. Subscribe for more fundamentals nobody teaches.